Susan. Good morning, everybody. Thank you again for attending this seminar. This is the second of a series for this semester, and we are very pleased to welcome Dr. Mukherjee, who's a senior R&D scientist associated with Oak Ridge National Lab, which is in Tennessee. We have quite a number of you who have signed up, and so I expect an audience of maybe 50 to 60 who will actually attend. So the topic is the theme of our entire seminar series is about large loads, and large loads, obviously things like data centers are causing quite a stir, for the community, because the amount of computing that is requires our industry, the power industry to grow really fast. And this is where the problems do come in, where the industry is not used to such fast growth, and so it's a very interesting how this is evolving. Every day there's something in the newspaper about rates, electricity rates, about data centers, and of course the big seven, as they call the magnificent seven, the seven drivers of this phenomenon. And Dr. Mukherjee is so qualified to talk about this, and the title of his talk is Flexible Load and the Electric Grid, a Bitcoin Story. And I thought this was a fascinating title. So Dr. Mukherjee is a senior scientist with Department of Energy's Oak Ridge National Lab, and also with a joint professor appointment at the University of Tennessee in Knoxville. Srijib comes with 35 years of research, engineering, academic, and management experience in climate science impacts to electrical power system operations, energy markets, energy storage technologies, and electrical vehicle transportation adoption challenges across the globe. He has an MBA in finance from Duke University, Fuqua School of Business, I believe, a Ph.D. in MBA in finance from Duke University, and a Ph.D. and an MSE from the University of Miami, and a BE from the Manipal University. He's a U.S. licensed electrical engineer as a professional engineer, is also a NERC certified grid operator, licensed to operate the U.S. electrical grid. Well, welcome, Srijib, and the floor is all yours.
Thank you, Professor Shankar. Thank you, Professor Shankar and Susan, for inviting me for your wonderful seminar series on load flexibility at Lehigh University. It's a wonderful engineering school, so thank you for inviting me. The topic, as Professor Shankar mentioned, was it's associated with a fascinating phenomena that we're actually seeing on the electric grid, associated with flexible loads. And flexible loads is a form of controlling demand in various forms. But today I thought we'd talk about a fascinating piece of load flexibility, and that is Bitcoins. I know often Bitcoins and crypto are not very well understood, and neither do I understand it very well. But at least I'll try to share some knowledge of what I think is happening. Okay, so let me do this. Okay, so we've seen the Bitcoin industry pop up quite significantly in the US, specifically in Texas. So when we talk about Bitcoin as a whole, it's basically we have these miners. And what are these miners doing? They're working on a digital ledger, which sort of has these blocks, what they call Bitcoin blocks, and um, and they do it with a Bitcoin machine. And that is like an ATM device where you can buy or sell Bitcoin with cash. So it scans your wallet address, inserts your money, and then you purchase crypto. And it's super, it's like a peer-to-peer exchange of actually trying to mine for these so-called puzzles. But it's very, very energy intensive. So when you mine for it, you could mine for it. You can have a big mine. You can have these big machines, processors or GPUs that actually are very, very energy intensive, and therefore they cause problems for the grids in the form of large loads. But the good news of this is the difference between a Bitcoin mining farm and a data center is a lot of data centers are inflexible loads. So they're 24/7, 8760 online, while a data center can can be flexible. It can go on, it can go off to make money for itself. Okay, so they look like a data structures. These are very, very, they're self-explanatory, so I won't go through those. Let me go to the next slide. So why is this topic of importance? It's a large source of demand on the US grid, so it is causing problems. It is an opportunity for business, for coordination with electric grid operators. And then the pricing of Bitcoin mining operations is very elastic from your purchase power agreements that you might have with a wind farm or a solar farm, which has a clear market clearing price with, let's say, dollars per megawatt hour, and the amount of revenue that you might get by behind the meter Bitcoin mining. So those are two different concepts. So purchase power agreements to sell to the grid, and then to mine behind the meter as acting as a load. And it's operational, which can be, which causes frequent amounts of curtailment across the system. Um, if you look at it in terms of research, there is a lot of uh, lack of Bitcoin mining research. So it's a very emerging area, especially in power systems, in energy systems. And how do we understand this in terms of resource adequacy? Resource adequacy, generators in the bulk power system, generators behind the meter, so integrated resource planning also behind the meter also. And then what is the expected revenue? What are the challenges associated with it? The magnitude of curtailing, and then the lack of understanding of what Bitcoin is. So I'll try to share some of that. Professor Shankar, are we going to ask questions at the end of this, or do we answer it in
Yeah,
between?
normally we do it at the end of this
Okay.
presentation, so it doesn't drop. So it's just your choice, though.
Absolutely. Whichever way, if people
Okay.
prefer asking an urgent question, I don't mind answering them at all.
Okay.
Yes,
We,
it makes it more interactive instead of
okay.
it just being a few boring slides that I might present over here.
Okay, students, if you have an urgent question, please go ahead and ask the question. But
Yes.
we'll wait for the talk to end for all major questions.
Thank you so much. Thank you so much. So let's give you a little bit of a primer, a bit of a background on what is a Bitcoin machine. I already talked about it. It's like a little bit of an ATM machine. And it works off an algorithm called the SHA-256. So what is an SHA-256? It's basically a one-way math function that Bitcoin uses for security. So it's like an input that spits out a fixed 256-bit hash. So the word is hash. And this 256-bit hash is converted. I don't know if any of you are computer scientists or computer engineers. I'm not, but at least I can try to explain it from what I I'm a very old engineer. I graduated some 37 years back. So a lot of this, I'm going back to old school things. So for example, the 256-bit hash gets converted to a 64 hexadecimal. So 64 hexadecimal is typically you would have the letters A to F and the digits 0 to 9 in a string. So it's if you change any one bit of those, the inputs, the output to, completely changes. So the miners tweak each one of those numbers. In tweaking each one of those numbers or alphabets is called a nonce, Nonce. And I hope people have heard that in what they call the blockchain process. And the whole process is sort of secure and decentralized. So how do you get paid for this, for this SHA, what they call the SHA 256? Um, no, what they do is it has a fixed length string, so the output from this 256 is like a digital fingerprint that you would have. And each miner measures the computing power tied back with that, like how many hashes per second they can crank out trying to solve these puzzles. So more hash rates means what does it mean? More hash rates mean a faster chance of validating one block. You get paid by block, and each of those 10 years, those blocks halve. I'll explain the halving process, but it isn't tied directly to the Bitcoining machine, but it's used for trading the crypto with cash. So not a nonce, like I explained, is just a random number that a miner would use to block a hash until it hits the right target. So you're trying to solve a puzzle with different knobs. And the more computational power that you have, the quicker your ability will be to get to what they call terahashes. So that's what it is. And everybody understands what a 64 hexadecimal is, correct? So one bit is 8 bytes. 8 bytes is 32. So if I 256 divided by 8, you have 32. So that's converted into 2 hexadecimal, that converts back to 64 hexadecimal. Um, so that's what you get. So now let me talk about a very important aspect of this. I absolutely hate reading through slides, so I like having conversations. So how do you convert 1 watt to a joule per terahash? So that's the most. You see over here, you got joule per. That's a joule. Joule is one source of energy. So 3010 watts is being converted to 21.5. And you can see the terahash rates. There's S19XP has the highest hash rate. So obviously it's going to have the highest revenue gathering ability. And you can see S19J Pro has a lower amount of that versus M30S Plus. So each one of these changes, right? So 1 watt is 1 joule per second. And what is 1 terahash? A terahash is a trillion hashes. So divide the joules per second by hashes per second, and then divide 1 by a trillion, and then you'd get that divided by 10 to the 12th joules per hash. Now, I think this, if unless you sit down with a piece of paper, it'll be hard to understand what I'm talking about. So 1 watt is 1 joule per second, and then you convert that, which is 10 to the power 12 hashes every second. And then when you look at it, you can't use 1 trillion watts. That's completely nuts. So minus flip the ratio over, and that converts to joules per terahash. Okay, so that's how you would do that in this particular case, dollar per hash that floats what they call the BTC, Bitcoin price in dollars. And then it's issued to you with transaction fees and block fees. So this is in 2022, so my data is a little slow, was 6 cents almost, 0.61 terahashes per day. So let me go back over here and talk about where does hash price come from. So we talked about the word hash, correct, which is the 256 string, character string that's corrected back into a 64 hexadecimal string that uh, you tweak via trying to solve that particular puzzle that you're trying to solve using the computational needs of your computer. So one Bitcoin miner, they're attempting to find a Bitcoin block that's hashed with block, it meets the target difficulty. The nonce is basically just propagated through the mining pool along with the different nodes because this is peer-to-peer sharing, like a digital ledger. And then the total Bitcoin revenue per day, for example, on a 10-minute average block time, 6 blocks is, let's say you go 24 hours a day, 6.25 Bitcoins per block, and $16,000 per Bitcoin, and then plus 3% transaction fees, your revenue would be about 14.8 million. This is just an example. So there are ways in which you would do it, but the difficulty rate, as we explained it, is in the 32-bit string, correct? So it's 2 to the power 32 divided by the 600, which is given to the expected number of blocks that you would expect to have. And then finally, you come up with the expected hash price, which in this case is 6 cents per terahash. I know this is very complicated for power engineers or someone not looking in more from the mining side of folks, but it tells you the math. Sort of the math is important to understand. At least the math is fuzzy and it's hard to understand it. So there's no easy way to understand the math, but I'll try to make it easy. So let's convert this. We talked about converting 1 watt to 1 joule per second. So the hash rate for this particular case was 246. Bitcoin price was 16,000 with $60 per megawatt input power to each of your machines, right? We just talked about the machines in the previous two slides, right? The M30S, all these things, correct? These could be quad processors, large quad processors, networks, whatever you're trying to tie back. They're all energy hogs. So the machine efficiencies is what calculates the joule per terahash. And then what you do is you take the hash rate in the network, that what the network consumes, to determine the amount of watts of true power. Power is watts, right? Watt hour is energy. So the amount of gigawatts that is being consumed by each one of them. So what would happen if you double the machines on the network but kept the Bitcoin price the same? The question is that you would probably be able to you'll be able to mine out a hash at a quicker hash rate. So the rate at which you'd be able to mine is a whole lot quicker. So the chances of making a higher revenue is going to be a whole lot more. Okay, so blocks would start coming faster. You'd get them in 10-minute times. Then they would adjust, and then they would try to retarget every 10 minutes. So Bitcoin revenues basically mainly comes from block rewards and transaction fees. That's where you get your money. So right now, each block gives 12 points. In this particular case, in the newest ones actually have 12-point BTCs, or 12-point Bitcoins. And then it halves every 4 years. So whatever folks add to speed up their trades to calculate it, what you do is you take your hash rate by your total network, and then you get your share, and then that times the daily blocks, which is what I'm talking about here, right? And would be your total reward. And that can vary greatly. And what happens is that every 4 years, these coins, they control new coins into circulation. So one block per block is like 2009, it would go down to 25 and then 25 down to 6. So it keeps having actually 12 and a half and then 12 and a half down to 6. So every 10 years, the number of blocks that are out there halves to the number of coins being introduced. So blocks is a bunch of coins, correct? Think of it as like that. And a subset of that is a coin. All right, let's go to the next slide. So here is the halving schedule, okay? So what is the point of halving? Can anybody in the audience tell me why would you have? Why does Bitcoin have? It's basically it boils down to simple economics. Why would you have? The reason you would have is to build scarcity. So the demand for it goes up each time you have. So think of the orange line, correct? Oops, sorry. This is your percent monetary inflation. And the blue line is your Bitcoins. Okay, so the number of Bitcoins are going up, but your monetary value going down because each time you're having you're mining for a higher value coin. So scarcity creates demand. So it cuts your miner's revenue in half in dollar terms. Okay, let's talk about the trends. So different mining machines, right? We talked about the S19, the S19J, the M30S, the M20S, the S19. You can see the computational needs of S19 is highly low, while that in the machines per dollar amounts in a highly more powered X19 XP is a whole lot more. But remember, that's like an energy hog. So the S19 XP is a big time energy hog. And this is what miners are putting on the grid. This is what they're putting onto ERCOT's system in Texas. So more you put on, the more your revenues go down, but the chances of you making large amounts of money is large. So this is how Bitcoins in a broadened sense work. Okay. Now, so what do generators have to do with Bitcoins? So Bitcoin generators have got everything to do with Bitcoin, especially if you're tied back or you have a purchase power agreement with a renewable resource, a renewable resource such as wind or solar. And that is when you can bid in like what they called a price taker. I hope everybody understands what a price taker is on the electric market. So price takers are generators that bid into the electric market at $0 per megawatt hour. So wind has no fuel cost, correct? Solar has no fuel cost, correct? So they bid into the market at $0 per megawatt hour. And they also are what we call a price influencer. So the renewables, when stacked against, let's say, a natural gas power plant, can skew the price in one direction or the other. Now, what the price that I'm talking about is the market clearing price. So there is a cost curve that's put out every day by these big interconnects, the PJM interconnect, the Midwest ISO interconnect, the New England ISO. Each of them have a price curve that comes out. And then each of the generators that are out there on the grid, they bid in at a marginal cost to that particular thing, to that particular curve. That curve is based on uh, the system's constraints and the system's congestion. So you could have T&D, transmission and distribution congestion. You could have generator redispatching. You could have outages. That determines whether you can push your energy out and deliver it or not. So think of it like Walmart and its products, right? In the electric market, what are we selling? We're selling watts. So in Walmart, what are they selling? They're selling eggs, for example. But to deliver those eggs from the warehouse to a grocery store, are the roads clear? Are they snow-filled? Which routes are blocked? Which routes have been washed away by a hurricane? That's congestion for you. That's exactly how the grid works and the same things. Now, these load resources can act as generators too. So we have these things that work behind the meter. One of them is a Bitcoin miner. Another is what we called a virtual power plant. So many of you might have heard of virtual power plants. Those are becoming grid resources. They're not grid. Grid is part of the network grid. Behind the meter is on the radial system that might be behind somebody's house or somebody's business or something else. That is a behind the meter generator. For example, my home is a small generator because I have rooftop solar and I have a Tesla Powerwall battery. My battery is a virtual power plant. When the grid needs it, they can use my battery to help support demand in the local area, demand as in load, help support load in the local area. So when they do that, they compensate me back for it. I charge my battery pack to power my home for free from the solar PV rooftop that I got. And there's a management system in how you do it. The same thing with Bitcoin miners. They can they can mine at 3 o'clock in the morning. They don't need to worry about on peak and off peak and all of these things. So if the grid operator asks them to reduce their demand, they can shut their mining operation down and get paid for it. If it makes sense for them to get paid for it from the grid, then they shut that mining operation on. So that's what we call a flexible load. So they're literally a flexible generator in terms of load to the grid. So the miner comes in. I'll show you an example where he has a purchase power agreement with a wind farm, with a solar farm, or any other entity. And based on how he mines, he can make money. So if you look at this last bullet, miners are exposed to nodal pricing and wholesale pricing, the same type of pricing that generators receive. This price goes through a couple of layers of hedging and aggregation and abstraction before it gets to industrial loads and residential consumers. So these layers are why residential customers are able to pay a flat rate associated with whatever expectation they have. So this is one of the reasons of how you can use your Bitcoin mine as a generator to get revenue for yourself. Okay, let's think about a math exercise in Bitcoin mining, okay? And I'm sorry, power engineers love math, we know that. We all do. It's a fun exercise, right? So think about it. You got a Bitcoin machine to calculate dollars per megawatt hour rate. Similar to how each of the generators have a bit curve, correct? How their bit curve is based on the generator's heat rate, which is their fixed and O&M costs, operational and maintenance costs. They must submit those to the grid operator on a daily basis, on a day-ahead basis, and which is the day-ahead market, or they can do it on the spot market with, and they can make adjustments as necessary. Bitcoin machines can be abstracted or taken into a dollar per megawatt value, and then that they turn into energy. This number is typically a break-even price. So the cost at which they stop being profitable with the generator and they make more money just mining without taking anything from the grid. So they just do behind the meter and stick to the behind the meter application of supplying their Bitcoin farm. So if you look over here, you have these models, correct? The terahash load, the terahash, which is the 256-bit string. This is what you're looking at, the hash rate of 110. S19 Pro is the quickest. That this has a 1.3 kilowatt load, but look at the load difference over here, 3.2. This is 308 machines, but a larger load. You have 1.3 kilowatts, but more number of machines, of Bitcoin machines. So your terahash per megawatt, of course, is going to be a whole lot larger. And your dollars per megawatt is only $93. But if you go to a more powerful machine right here at the bottom, obviously, even with a lesser number of Bitcoin machines, your computational power thing is a whole lot more, and therefore you make more revenue. So that kind of gives you a sense as to how this can be mined or this can be done. Okay. So mining behind the meter. Let me talk about if you had to mine behind the meter, if a load is connected behind the meter of facility, what is the change? What changes is the net megawatt flow that you would have back to the transmission network. So for example, if a crypto miner connects a 10 megawatt Bitcoin mine that's behind the meter at a 100 megawatt solar facility, then the grid operator would see that as a load, negative 10 megawatts at night. 0 megawatts is coming from the solar panels at night, but it's actually producing 10 megawatts. And 90 megawatts during peak, because it's a 100 megawatt facility, so you're getting 90 megawatts at peak production when the panels are producing 100 megawatts during the day. So what impact does behind the meter Bitcoin have? Let's take a look at that. So this is a little complicated, but I'll go through it slowly. I'm sorry it's a crowded slide. Okay, so, and then I'll show it to you in a picture because it kind of gives you the idea of explanation of how a Bitcoin mine examples. And, countries and nations are using this. The little nation of Bhutan makes money right out of this in this particular fashion. One of my classmates from Duke is on this call. I hope he is. He runs the system for Bhutan, and they make billions of dollars. And so you have solar and wind. Node price is $0. You have a city node of $36, and you have a combined cycle node price of $36. So in this example, you got a 15 megawatt and a 10 megawatt Bitcoin mine connected behind the meter, wind and solar farms. Note that the wind and solar farms produce 60 megawatts. Their rating is actually 60 and 40 respectively. So the grid operator only sees the market net of the output, which is 45 megawatts. So 60 minus the 15, which is from the miner, right? So 45 is what the grid operator sees from your machine and from your farm, and 30 megawatts in the second case, which is the 40 megawatts minus the 10 megawatts that you're actually doing for your Bitcoin mining farm. And this example, we're going to use $30 per megawatt hour and $25 per megawatt hour for your purchase power agreement for the behind the meter mines. So you take this, you have a revenue stream that is insusceptible to curtailment, so you're not subject to curtailment and grid pricing. And then what you do, as the grid operator can only curtail or pay megawatts that impact the grid. He can't curtail you because of your load. If it impacts the grid, then he can curtail you. So if a generator is netting 0 megawatts at their point of, if they're netting it at 0 megawatts, then if they're netting your system at 0 megawatts, then it's your load. The problem is your load. Your Bitcoin mine is the problem, not the grid. So you got to watch out for that. Now, let's say the generator is earning some amount of revenue during curtailed hours. It can price the grid, which faces the purchase power agreements, lower, so it can price itself in the spot market lower in order to win the RFPs. Now, if you, of course, if they're sourcing it through a price influencer generator or price taker generator, which is a renewable resource such as wind and solar, it doesn't matter. But if it's a natural gas, it does because it does have a fuel cost associated with it. So, generators, as you know, are usually interested in low risk, low return contracted revenue. So the project returns are usually fixed around a target. And then they're optimized for potential, whatever amount of whatever targeted returns it's expected to have. And then finally, what it is, it's monetized to reduce the contract revenue pricing within the purchase power structure. This is a little hard to understand, but in the diagram, I think you'll see it a whole lot better. If the grid pricing becomes lucrative than the Bitcoin mine, then the generator and Bitcoin mine can coordinate to turn off the mine. This is exactly what I was talking about. So let's say you're making more money out of the grid on the electric market. Just put your Bitcoin mine off. You don't have to mine. If you deliver more megawatts to the grid, then that revenue, all that proper coordination will go to the grid operator. Why let them have it? You can take that for you because they pay you back for that. And for the hours that site is a net load, then the miners will have to procure from the grid. The mine can hedge its exposure to prioritize co-locating with wind or thermals, and then they go behind the meter and just work their Bitcoin mine. So it looks something like this. This is what it looks like. Okay, this diagram is really important. So think about it. Wind, we talked about it, produces 60, it delivers 45 because of the 10 megawatt load. 15 megawatt load. A 15 megawatt load is part of the Bitcoin mining load, which is what it is. It bids a zero. Why does it bid a zero? It's a price taker. It's a wind farm. So the congestion price, which is the market clearing price, right here, the market is clearing at $36 per megawatt hour. Okay, it has a shadow price plus the shift factor is zero. So zero from the grid, you're actually making zero from the grid in this case. But how much are you making out from your Bitcoin farm? You're making $450. Think about the example with the solar. Solar is producing 40. The farm has 10. So you subtract that. That's 30 megawatts to the grid. And it's curtailed only if it's curtailed down to, okay, so let's say the grid operator decides to curtail solar down to 20 megawatts. It's a price taker. So therefore you bid it in at $0 per megawatt hour. The congestion price is the same price as the wind because in the same market at 36, that's the market clearing price, which is the congestion along with the transmission lines that reduces wind and solar. So that's $36 per megawatt hour. And in that particular case, you get paid nothing from the grid because you're solar. But out of your Bitcoin farm, you're making 250. Now, on a normal operations, let's say this guy, he doesn't have a Bitcoin farm. He's a natural gas combined cycle. Oops. And here we go. The natural gas power plant guy. What does he do? He has 50 megawatts to sell. So he produces 50 megawatts. He bids in 36. So they dispatch his generator and he makes $1,800. So this is how the concept of this flexible load works in front of the meter and behind the meter. And it's literally a business. So with that, I took about 40 minutes. I'll leave another 20 minutes out for questions. And if anybody has questions, anything.
All right. Thank you, Srijib. Questions for Dr. Mukherjee? I'll have the students take the first shot at the questions, please. And when you have a question, please introduce yourself and ask the question. Students?
We have a question.
Hi, thank you so much for your presentation. My name is Selena. I am part of the ESE program. And I was wondering, I looked it up a little bit and it says that Bitcoin is like a user to user, like you said, where you share encrypted money. So
Mhm.
how did that ever translate to going to the energy market?
Well, uh, translating to going to the energy market, that's a very good question, my friend. Thank you
Thank
for asking
you.
that. So when you let's say at your home happens to be, let's call your home an energy market. Oh, sorry, not an energy market. Let's call your home a Bitcoin mining farm. So you're mining, you've got computational power, you're mining. You lose money because your computers are big time energy hogs, right?
Mhm.
So you have the flexibility, you have the flexibility to mine whenever you want. You can mine at 2 o'clock in the morning or 6 p.m. in the afternoon, evening, whenever you want to do it. You can do it, right? It doesn't matter. So now, if I know that my particular, I have a purchase, let's say I hedge myself and I have a purchase power agreement with a nearby wind farm or a nearby solar farm, which is a grid generator, right? Not a behind the
Mhm.
meter generator. And I have an agreement with them that I'm going to I'm going to sell back to the grid if it reaches $36 or $40 a megawatt hour. Then it makes sense to shut my 10 megawatts of Bitcoin mining down to get it at 36 or $40 a megawatt because I'm making more money out of the grid by being a flexible load. That means I'm shutting myself off. So think about it like this. If everybody's selling eggs, right? And at $5, I don't know, egg prices have gone down $2. Let's say $2. And all the roadways are congested to get those eggs to the grocery market, right? And your your eggs adds contributes to meeting the demand for eggs that are out there. You say, well, guess what? I'll let the streets of congestion reduce, but you're going to have to pay me $5 instead of $2 for delaying the delivery of my eggs to the market. Does that make sense to you?
That makes sense to me. I'm just confused on where Bitcoin comes into play with everything.
Bitcoin is just mining. So what you're doing is you have this 256 character string, and now I'm not a Bitcoin miner. Okay, I'm the old school S&P 500, Dow Jones, Gordon growth formula for my shares, getting dividends. That's me. I'm just old school. But Bitcoins, right? I don't even know how it's mined. But my understanding of it, this is my understanding, is just that you have this little hash. It's 256-bit, looks like a 64 hexadecimal. And then each one of those are like one blocks. And then what you do is you play with those letters or blocks and target it to something on that ledger, which is what they call a nonce. So when you hit a target, which is very difficult to do, you have to keep mining. The higher the speed of your machine is, the quicker you can actually, because everybody's connected. You've got a million people all over the world connected. So it's peer to peer. So you're trying to mine through this. And when you hit that, then that particular that particular coin becomes yours. And then it goes into your purse, which is your ATM machine. It's like your bank account. It goes into your bank account, and then you can convert it to cash or dollars or whatever you want, and then and then do it. Now, this is different from meme. I think meme coins, the volatility of meme coins are based on popularity. So if I happen to be Dwayne the Rock Johnson, and I am really popular with my wrestling. People go, "Oh, I like him. I'm going to buy more of his meme coins." So fame and thing determines. So it's all hearsay. So So that's what does it. So you float a meme coin, like the Kim Kardashian meme coin will probably influencer. I'm not familiar, but I think it's called influencer. So that influencer would probably make more money off of that. Yeah.
Okay.
All right.
Thank you.
You're most welcome.
All right. A follow-up question on that. My name is Panache. I'm
Yeah.
also part of the ESE student.
Mhm.
So my question is following up on what you just said. Like, we are being paid once you reach your target. Let's say you started mining in the morning, you
Mhm.
reach your target, let's say around 3 p.m. Then you
Mhm.
say, I will mine again starting 6 p.m. So
Mhm.
as in the meantime, I'm going to shut down my computers, right?
Yes.
Then you get paid for that period that you shut down your computers.
Yes. Yes.
So can we say it's like what happens in the capacity market where the utilities are being paid to power on their generators so that they can meet the demand?
That's correct. You explained it better than me, my friend. Well done. That's exactly it. That's the
All right.
whole concept.
Thank
So
you.
you being flexible, you get paid for being flexible, okay? If you have
All right.
co-located generators like data centers do, correct? With the
Mhm.
AI data centers, if you let's say you're a data center and you want to make more money, of course, Google and these Max 7s are deep pocketed. They don't care much for money. So, but you just happen to be a smaller data center and you want to make money, then you can become flexible. Put it off. Let put it on. Whenever you can make money off of the grid, make it. Or you can have a co-located generator that can act like a black start unit to serve the grid from behind the meter. Then that's what it is. Just remember that the electric grid across the world is becoming exactly what Professor Shankar is trying to talk about, and he talks so much about, is moving to a decentralized architecture. We're no longer going to be, I mean, industries are going to make their own little things. Cooperatives and housing is going to go on their own little thing, and they're all going to work peer to peer. But the advent of networked grids and pooling and all of that is winding down.
All right. Also, to add to that part, in as much as I know about Bitcoin mining, I think it's very difficult to mine, like, let's say, for example, one Bitcoin
Mm-hmm.
as an individual. So like
Mm-hmm.
you say, they do peer to peer. So let's say we combine, like, people in this room, so that we win like partial prizes. So let's say we are targeting 3 Bitcoin, all of
Mm-hmm.
us.
Mm-hmm.
So we are working on it together as a team.
Mm-hmm.
So during that time, let's say I mine my share, then
Mm-hmm.
I can switch off my computers, then later another
Yes.
one, mine, so that by the end of the day, probably we mined at 4 different times during the day,
So
depending
smart.
on, yeah. So
So smart. Exactly. It's sequential. Exactly.
yeah.
Instead of
So
doing it in parallel, you do it in sequential.
okay.
That's very strategic. And a lot of the firms that are in Texas, Bitcoin mining firms, they're actually energy companies. They claim to be energy companies, but they're Bitcoin miners, do exactly that. So it's very strategic. You do it sequentially on time blocks.
Exactly.
Yeah.
All right. Thank you.
You're most welcome.
Hi, my name is Bintusila. I'm also part of the ESE program. So my question is, apart from shutting down to help reduce the peak demand, what else can the Bitcoin mining do to help support the grid?
Oh, let's say you had co-located generators, or let's say, my friend, you had a part of the grid go down. Then the Bitcoin mine can act as a black start, can act as if they had behind the meter generation or a virtual power plant. Let's say they had a battery storage. They can support the grid or help the grid get back after a cascading outage or a portion of the grid goes back. So not just under normal conditions, or let's say constrained conditions, but under abnormal conditions. So if an abnormal switching condition, or let's say a breaker failure happens somewhere, and let's say the Eastern interconnect separated from the Western interconnect, or we separate from the ERCOT interconnection, Bitcoin mines can definitely have agreements in place to support re-energize the grid from black and get paid for it. Even those assets could be standing assets not being used for anything. But just like data centers, they can be used for that particular thing. So that's one application right there.
All right, thank you.
Yeah.
Anyone else?
Questions?
Yeah, I have a question. This is Zahra Shimari from Lehigh ESE student.
Yeah.
How can the Bitcoin mining act as a flexible load for the power grid?
It's not per se the Bitcoin mine, but the computer that mines it. So for example, I was showing you on my slides, right? The S19, S Plus, M13, X Pro. So each of those have processors. So each of those processors have high computational needs. So more intense processing, more number of processors you add, the quicker you're going to be able to mine, which means the possibility of getting a higher revenue, higher Bitcoins, BTCs, is going to be higher. But when you plug in more computers, it's like your house. Think about your house, right? If you
Yes.
had one laptop, that's fine. But if your husband and you and your children and their friends all plugged in, then that's more. You see what I'm talking about?
Yeah.
So you're becoming that. So even like having wireless repeaters in your house, if you have 10 people on wireless, it's going to be a little slow.
Exactly. Thank you.
You're most welcome.
I also have a question. My name is Kevin. I'm in the ESE program as well. I know you're talking a lot about Texas, and I know that's because of the relatively deregulated market. Is there anywhere else, either in the country or in the world, that has markets that are lucrative for Bitcoin? And if so, is there anywhere in the US where that's
Great
leaning towards
question,
next?
Kevin. Okay, let me ask you, where do you think? Where do you think is the most liberalized and deregulated market? Go ahead.
In the US?
In the US. Go ahead, say it.
Outside of ERCOT, I would say SPP, MISO.
Go west. Go west. Where is it?
California.
California.
CAISO.
There you go. California has the most open market conditions that'll happen. They have the most renewable resources available. So some amount of Bitcoin mining has happened in California, but California is a fully deregulated market. The growth of data centers has been very extensive in Virginia, and Virginia is also looking to do Bitcoin mining too. But Virginia is tied back with DC, so data security, data encryption, cybersecurity, and all those kind of Loudoun County, especially data centers have become really super, super critical. Up the Northeast corridor, that's where it is. But the most liberalized deregulated market, beyond Texas is definitely California, and it's up and down that particular. The state of Washington, Oregon is the same too.
Okay, thank you.
You're most welcome.
Okay, questions from the audience? I have some in the chat box, so I'll go through them, Srijib. Joe Andresani, he asks, how does the investment and the cost of servers, HVAC, personnel, land, etc., compare to the cost of the energy used by the servers?
Oh my gosh. If somebody from industry asked me that question, who asked me that question? Professor Shankar.
Yeah, it's Joe Andresani, and he's one of my colleagues from college for 50 years ago. So.
That's a really good question. I don't, my answer is I don't know. That's a really, it's power usage efficiency versus, let's say, water usage efficiency in a data center. I don't know. How many? I think if you do like parallel computing, it has a certain cost factor, but I can't remember it off the top of my head. I think in comparison to, let's say, a 5 kilowatt load for an HVAC system at your home, um, I would say the computational needs for parallel computing is a little lower than how much HVAC takes in, but more efficient HVAC systems right now would probably be more expensive. I don't know the exact numbers, but for example, on 11.5 kilowatt or 13.5 kilowatt hour load, um, uh, about 1 to 1.1 kilowatt goes off in your HVAC systems, and your computers will not really need that much. They'll probably be 0.5 or 0.7. I would assume that much. I'm just going off of the top of my head, but that's a very good question.
Okay. Another question I have from Alejandro. Given that Bitcoin mining is highly elastic and revenue driven, how should market rules be designed to distinguish between speculative, short-term mining operations and those that can reliably participate as controllable demand response resources? Are capacity commitments, minimum availability requirements, or contractual curtailment obligations necessary? Long question.
Oh, another very, very good question. So most miners tend to have firm contracts or what they call firm purchase power agreements. Um, to whatever agreements they want to have with the generator that they want to buy or sell from. So, well, basically, if they, let's say it's a 10 megawatt wind farm and they decided to purchase 5 megawatts 24/7, and the 5 megawatts belongs to them whenever they want to dispatch it out. Market rules right now in the day ahead market is based on a bid curve that allows these operators to run what they called a security constrained economic dispatch SCED. So they run a SCED that tells them where the system is constrained, where curtailments are happening, where these events are happening, and that determines a market clearing price. Individual generators, individual entities, and merchant generators who are actually competing in the market have to do the analysis themselves to bid in at whatever price they want to. So that creates a pretty non-biased electric market. Now, this non-discriminant market doesn't exist in the Southeast. We are the only one that does not have a regional RTO or an ISO. The rest of the country has an RTO, ISO, and they each are joining up in different. For example, California is joining up with SPP, the Southwest Power Pool. So the market rules in terms of load resource management generators. I call them flexible loads. Those have to be defined. Now, the new FERC ANOPR for interconnects is coming out, and the new FERC ANOPR will have a lot of these things that are going to be eventually addressed into market pricing with behind the meter generation, including Bitcoin mining, virtual power plants, and other applications that are coming out. That's as best as I could do with this answer because I don't know the full details how to answer it in terms of capacity and policy issues.
Hi, it's Bintusila again. I have a quick question. You mentioned that Bitcoin mining computers can help with black start in an event of abnormal service interruption. And this bidirectional flow poses a safety risk. So is there any safety risk management in place to avoid those risks?
Oh, yes. So part of the interconnect agreements for the farms has the safety risk covered in that agreement itself. So it should connect. You can't, if it's a co-located generator, if you have a co-located, let's say you're a co-located virtual power plant in the form of a battery, that battery it's considered a non-grid battery, right? But if it is behind the meter and you want to connect it to the grid, it has to meet certain conditions before the sensors, the communications allow it to interconnect back up. Those safety measures are in place. It's not like hooking up a diesel generator when a storm happens in your garage.
Okay, there's a question from Yuanji Wang. This is all in my mind too. Can you comment on mining versus data center? Are they competing each other since they both consume a lot of electricity and water?
Very good question, my friend Janjing. Very, very good question. They are both, Professor Shankar, they're both big time energy draws. But to me, data centers are more of a challenge. And in terms of land use, in terms of my former colleague, I hope he's here. He's a really bright guy, Shailesh Jain. He had outlined power usage and water usage. So GPU count for data centers. Typically, data centers don't want to be flexible. So if they're inflexible, non-curtailable, then co-located generation is super important to them. Bitcoin mining is a true grid player because what they're trying to do is say that, hey, I'm as flexible as possible. You can take me off and I don't care because I know how to make money off of you. So they're a business. The data centers, no matter what, usually the hyperscale data centers have to be on for AI needs 24/7, 87, 60 hours. So that's why supporting co-located generation with data centers with, let's say, SMRs, small modular reactors, and nuclear makes more sense for their regulating needs versus that wouldn't work for a Bitcoin mining operation.
Okay, any other questions from the audience? Please unmute yourself and introduce yourself and ask a question or put it in the chat box.
I'm no genius at this topic. I'm just learning myself. So please.
So Dr. Wang asked an interesting question. Is one of the takeaways from this presentation, Srijib, is that the blockchain, the Bitcoin industry did something smart, and is the message that data centers should look at a strategy along those lines?
Yeah, I absolutely think so. Dr. Wang's question is very relevant. If data centers can align with the kind of policies Bitcoin mining has done within Texas and now into California, it could lead to good policy for interconnects with data centers. I'm 100% on board with that. So the way you interconnect, the way you define your usage needs, and if you can clearly, if you can still be semi-flexible while not being flexible. So you get butter on both sides of your bed partially. And we can reduce interconnect times of how, like Bitcoin, for example, a Bitcoin farm, to interconnect a Bitcoin farm is so easy. They don't have to go through the 2 to 3 year wait cycle like data centers have to do, or 3 to 5 even. because of the laws, the permitting, the regulatory needs, the policy needs, the system impact needs, the network upgrades needs. These are the load resource managers. They don't have any needs. They just have a couple of computers that they're adding onto the grid, but they're passing on the network upgrade costs back to the load. So data centers have to cover the network upgrade costs. A Bitcoin miner would, but his would be negligible. So in my mind, I think data centers can take a page from Bitcoin, from the Bitcoin mining community in a lot of its applications to interconnect.
Okay. Any questions for Dr. Mukherjee? So again, follow up from this question that Dr. Wang kind of started off with. So another takeaway from this is that, hey, we've had this Bitcoin industry for a long time. We never complained about, not having enough growth. And now with these large loads coming in from data centers, is that a message that the Bitcoin industry has done something that the data center folks need to follow?
What a great question. Everybody has, you and I know this, Professor Shankar. We've been around the grid a long time. This is my 37th year on the grid. Resource adequacy is not a challenge in the United States. We've got plenty of generation. We don't need to build any more. It's our untapped generation that we are forgetting. And that's exactly what you were bringing up. What's behind the meter? Decentralized DERs, distributed energy resources, decentralized distributed generation, decentralized microgrids, decentralized virtual power plants, and the resource adequacy challenges go away. So what the Bitcoin miners were doing was sufficiently enough for the wholesale grid generators to manage. But now the wholesale grid generators can't manage these overexpensive 20 to 25 megawatt data center loads, and they need generation from another source. Well, go behind the meter. Look at all the decentralized inertia that's out there, whether they be inverter-based resources or whether they be rotational inertia. They all contribute back. So think about it of bidirectional flow. We no longer work in an interconnected grid. We work in a distributed grid. And until that concept becomes clear to everybody, I think we'll continue to have this challenge and in trying to solve this. At least that's the preaching point that I have, that I try to, and not that I'm selling anything, but that is the preaching point that I'm trying to explain to younger engineers and younger researchers, that we got to broaden this to explain it in that fashion.
So has this been kind of presented to the powers that could make a difference, like DOE or hearings in
somewhat
Congress?
getting, Professor Shankar is slowly getting through. It's a real slow process. So the process has been slow, and instead of investing money into infrastructure, constant building of generation, T&D infrastructure, and all these kinds of things, we're not utilizing our existing resources properly. And that, in my mind, has to be addressed, to look at this in a broader fashion, because it's reaching an inflection point because of ratepayer energy prices for ratepayers are really going through the roof because of this. So one or the other has to give, and somebody has to understand it. But it's been very slow, Professor Shankar. It's been looked at, but it's very slow.
Wow, this is good. Any question? We got some time to ask questions.
Yeah. Have I confused all of you enough?
No, I think people have been really been stimulated by this.
Okay, I'll put my face up so you don't have to see my face there. I'll stop sharing here. There you go. You can see my face then. Oh yeah.
Let's see. Any other questions before we stop? Any final questions for Dr. Mukherjee? Well, Srijib, you just made us all think differently. I came here knowing nothing about Bitcoin and mining. I thought, oh, it was kind of a nice alternative for regular dollars and cents, but something there's a lesson to be learned that could be carried forward. And I think that message itself is very strong. Thank you again for your wonderful presentation, and thank you.
Thank you for inviting me. Thank you.
Thank you for being flexible. You're supposed to come last week, and you agreed to be doing it this week.
No, thank you to you, Susan, and all your students at all your electrical engineers. Good luck graduating from a wonderful university, and to everybody who's joined here. I'm at the latter end of my career, so I'm just trying to promote to make things better. And I'm no guru at Bitcoin mining or anything like that, but I do understand the grid.
Yeah, that's good. Well, that's key right now. Thank you very much.
Yeah, that's right. Absolutely.
Thank you very much, Dr. Mukherjee.
You're most welcome. Take care.
Okay.
Thank you so
All
much.
right, take care. And
Thank
we do have
you.
Thank you, Professor.
Thank you.
you.
You're most welcome. Thank you.
Thank you, Professor.
Bye-bye.
the next week we have a seminar February 9th, I believe, and it'll be about the ERCOT grid. So there we go. So more on the ERCOT grid where they deal with such problems. So thank you very much. Stay tuned for next. I hope you come in. You're able to attend next week's seminar, and hope to see you in future seminars. Thank you.
Thank you, Professor.